Yeah, don't touch it too much.
Am I moving up and down now through the file?
Yeah.
Yes, you are.
So I'm on, this is the first page, right?
That's your title page. Yes.
Okay. And then that's not the title page.
That's the second page.
Okay, good. Okay. Now I'm ready.
Okay.
Okay. Sorry.
Sorry, everybody, for these technical difficulties, part of this modern war. So our next speaker is Mourad Ismail, and he will talk about q-Fractional Askey-Wilson integrals and semigroups.
Thank you. Thank you very much for the invitation. And when I first heard about it, I thought, you know, finally I will get to Argentina, but I guess I didn't. Okay. What I want to, so let me first remind you of how the semigroups enter this picture. So if you look at the initial value problem, so this is the partial differential equation with the initial condition. The solution of that, we all know from elementary PDEs, is this. So this is like, it's known as the Gauss-Weierstrass transform. And if I call this thing W acting on F at T, W of F and T. So this is now my transform. So it's acting on F, but then I have to evaluate it at X. And the uniqueness will give me a semigroup, in the sense that if I take this operator and I replace T by T1 and then act on the same thing with T2, what I get is T1 plus T2. And also, as T tends to 0, I get the initial value. So I go back and recover what F is. Okay, so from here, there is this general approach that we have a semigroup, meaning it's a one-parameter family of on the positive real line. It acts on some suitable function space. I don't want to get into that. And it has the semigroup property. If I act at time t1 on the operator at time t2, I get t1 plus t2. And as t tends to 0, I get the identity. Okay, so this is what this transform is. The next question is, what about this operator here? What is about this second order differential operator? Well, that turns out to be the infinitesimal generator of the semigroup, meaning if I take t at t plus h, I subtract t at t, so now that's an operator, I multiply by 1 over h, and let h tend to 0 plus. What I get is, because the semigroup property, this t of t factors out, and I get the same expression, but now at 0 instead of general t. So now I have the general positive operator, general the semigroup, and this is the infinitesimal generator, but at 0. So if I know the infinitesimal at 0 by translation, I can get it at any other point. So you just compute the infinitesimal generator at 0. And in the case of this Cauchy problem, that's what the second order derivative is. Okay, so this equation here says the infinitesimal generator is equal to the time derivative. Okay, so in general, now this is what the equation is, and this is what the value is. And the solution is this positive linear semigroup acting on F. Okay, now what about fractional integrals? How do they come into this picture? Well, there are two types. One is called Riemann-Liouville and one is called Weil fractional integrals. So the Riemann-Liouville is this one, and the Weil is this. And each of them forms a semigroup. This is this is how they're introduced in the first place. And they're adjoints to each other. And what's important is that if I take one of them and act with the derivative, it lowers the order by one. This is why it's a fractional integral. If it's an order alpha and I differentiate it, I should lose one order. I should go alpha plus minus one. Same with the Weil fractional integral. Okay, so this property is important, that I have this operator that I'm looking at fractional power, the fractional power of its inverse, and then I act on this, and then this property should hold. Okay, so when you have something like this, the first thing you want to do is look at the ranges of these operators, these fractional integral operators. Define where domain is and look at the range. They also act as multipliers for the Laplace transform. And the theory of multipliers for general transforms is well developed. And Erdely was one of the very active people, Rooney, McBride, Haywood, Kerman, Raffaello, Samko. So a lot of people worked on, on this multiplier theory. So multiplier theory means I have a transform, and this function here is called a multiplier if I multiply it by the transform, that is the transform of another function. Now you see, I don't know that this is a transform. Like if I'm doing Laplace transforms, I don't know that this is a Laplace transform of a function. Otherwise, this f will exist. This is a convolution. But in general, I'd like conditions on this in order that this thing becomes an operator acting on f. Okay, and the inversion formula for these operators is this. If I take the fractional integral of an integer order plus a, I try to cancel the a by taking a fractional integral of 1 minus a. So this here will be a fractional integral of order n plus 1. If I differentiate it n plus 1 times, I should get the function back. So this formula, proving it is another matter, but intuitively it's clear. Okay, but now what about other operators other than the derivative? Are there general similar theories? There is some stuff for difference equations, and for this q difference operator, the fractional order and so on, and q Laplace transforms were introduced starting from the 1960s. I think Abdi worked on this. Al-Salam and Verma wrote a couple of papers, and Nabin Mansour have a lecture note in Springer on the q-Fractional integrals with this operator. Okay, now there is another q operator, which is the AskeyWilson. So now I want to define what that is. Okay, so I do like the way you go from the interval to the circle. You replace x by z plus 1 over z over 2. Then if I have a function of x with this change of variable, it becomes a function of z. So now my original function as a function of x, to denote that I'm using the z variable, I use a check here. Okay, so that's what the function is. And what the AskeyWilson operator does is you take this f check and you dilate it with q to the half and q to the minus a half. And then you do the dilation on the identity function, e of x is x. If you calculate what that is, that's what this thing is. So this is like delta F over delta X. Now, it's important here to notice that this is symmetric in Q and 1 over Q. This old operator is not. This one is not symmetric in Q and 1 over Q. This is. This may look a little bit awkward at the beginning, but it's really the correct one. It really is the nice, the one that we should be looking at. Okay, so the Chebyshev polynomial of the first kind is cosine n theta. Of the second kind is sine n plus 1 theta over sine theta. It's a function of cosine theta. And what this operator does is if you act on the Chebyshev polynomial of the first kind, it gives you the Chebyshev polynomial of the second kind. And it reduces the degree by 1 and multiplies by this factor. And indeed, if you let n tend to 1, you will see that this side here reduces to the derivative of Tn. So as q tends to 1, the Askey-Wilson operator becomes the derivative. Okay, so once you have this kind of operator, you want to think about what the powers are, what the exponential functions are. Is there a Fourier transform? Is there a Taylor series? All this stuff is known. This, through the years, people worked on this. Okay, so let's go back to the starting point. We start with a semigroup of operators, and it has an infinitesimal generator. And then there is some natural operator where I act on the semigroup, I reduce the parameter by 1. That's like if I differentiate a fractional integral of order A, I get a fractional integral of order A minus 1. That's exactly what you want. So if this happens, then you know that this T is like a fractional power of A inverse rather, of one-sided inverse. So that's what this is. It just, this is like a power, a fractional power of one-sided inverse of this operator. Okay, so this is in general, this is something desirable to do. Now, what I want to do is I want to construct this TA for the Askey-Wilson operator in such a way that this happens when this variable, this operator here is an Askey-Wilson operator. All right, so the way to do that is through the Poisson kernels. So if I have a set of orthogonal polynomials, orthonormal polynomials, the measure is normalized, total mass 1. Then I look at this bilateral generating function. So it's bilinear, it's linear in x, it's linear in Pn of x, linear in Pn of y, and it's bilinear in the product. Okay, it says clearly bilinear. So this is the Poisson kernel. And its importance is, well, first of all, it automatically gives me a semigroup of operators. Why? Because if I integrate one of these at R times another one at S, what happens is that Parseval's formula make the cross terms integrate to a delta Mn, and then I get the variable now is R times S. Okay, so this would be a semigroup if I replace R by e to the minus t and s by e to the minus s, that would be e to the minus s plus t. So that gives me a semigroup automatically. I don't have to worry about it. I need to check that that this becomes the identity operator as r tends to 1, which is the t goes to 0. So, and this is also true, but this needs some assumptions that this thing is positive. If the Poisson kernel is positive, I can justify that. And on a compact subset. Okay, this is just Krofkin's theorem. It's not a big deal. Okay, so now here is what's new. I take the Poisson kernel, I replace the r to the n by something to the a times n. So this way it becomes additive in a. And I integrate against the function times the measure. But to keep it general, I multiply and divide by a function. Here I divide by the function at y, and here I multiply by the function at x. So I have to make some assumptions about the integrability now of 1 over g with respect to this measure. And, you know, I have to be careful. But this is always a semigroup. Formally, this is a semigroup. And the reason is as a tends to 0, this thing will converge to f over g, and the g cancels the g, so converges to f. Again, I have to make precise assumptions for this. So Suslov in 2007 looked at the case when there is no g. Looked at this case. And in his analysis, somehow he assumed that the functions he's acting on are analytic. Now, this is not a good assumption because usually you want things like an L2 or continuous, or because analytic is already very smooth. And what you want with these things is things that give you smoother functions than what you start with. When you start with something analytic, it's already very smooth. So, and he did this not in the generality, but when these polynomials are continuous Q-Hermite polynomials. The Poisson kernel in this case is known and it's non-negative. And we know then that this integral, if g is 1, this integral is going to converge to f for continuous functions in -1, 1. Not analytic, just continuous is good enough. And you can make it even weaker than that. So this is very simple. And he did not address infinitesimal generators or treat this as a semigroup or anything. He just was motivated by trying to find some analogs of Fourier transforms, and that was all he's interested in. Okay, so the approach I'm presenting is from some work with Ruiming, Zhang, and Keru, Zhou. Zhou just graduated, finished his undergraduate in China. And the first paper is submitted to Advances in Mathematics. We have the first freeze reports. We're revising it, and we think it will be accepted. So we will make the changes they wanted. So, okay, so in this first paper, so these papers are about studying this, the fractional powers of AskeyWilson operator, and looking at this here for different G's, and just see what is going on. Okay, so the first step, of course, when you have such an operator, you want the A that reduces the semigroup parameter by 1. And you would like this to be the AskeyWilson operator or something related to it. Also, you want to know what the abstract Cauchy problem is, the one that comes from the infinitesimal generator of this semigroup. Okay, so the continuous Q-Hermite, we took A to be the AskeyWilson operator, and the G that we chose was this function. This is like half a theta function. Or sorry, rather, if I take a product of two such things, I get a theta function. So this is, there is some, it has some very tricky structure. And you multiply the kernel by this for some reason, because if you don't, the operator doesn't become the Q, becomes something depending on the semigroup parameter, which is certainly a disaster. So if you modify it by multiplying by a certain factor, then the A is indeed dq. Okay, so for the Q-Hermite polynomials, this is the Poisson kernel, is explicit. So the variable, power series variables are, so this is a product, has no x's or y's, and this is a product involving x's and y's. So x here is cosine theta, and y is, I guess x is x, I left it x, and the phi, the y is cosine phi. Okay, so this is what the Poisson kernel is. So now I can write what this operator is. And after I write it down, it works. It does. It's a semigroup. You can prove it's a semigroup, and you can prove that for this choice, the operator A that lowers the degree is dq. If you look at the Suslov case, when G is 1, it's not the AskeyWilson operator. This is he gets a semigroup, but the A that lowers the semigroup parameter is not the AskeyWilson. It's a different operator which we computed. So we computed that, and it's a combination of this F checks. Okay, so how did this evolve? Originally, I had a paper with Rahman in 2002 where we wanted to find a one-sided inverse to the AskeyWilson operator. So we wanted an operator such that if I act with the AskeyWilson operator on this, I get the identity. And to construct this, originally there was, the first time that this was done was in a paper with Ruiming Zhang in the 1990s. And with Rahman, we did it for L2 weighted with the AskeyWilson weight. The original paper with Zhang had the Q ultraspherical weight. But with Rahman, we had that. And also we didn't have explicit formulas for the kernel of the operator. But Rahman, of course, was a wizard at these things. So he computed the kernel. You can identify the operator, the dq inverse, as an integral operator, and we computed the kernel. And the kernel was exactly this thing with the G given by this G. So this is in the paper with Rahman. Now, once you know that, the next thing you do is try to raise this to some powers, raise it to, to square it, cube it, etc., and so on. When we did that with Zhang and Zhou, that's how we found out that this structure works. This structure works with the specific G that we found. So we first checked it for when the power is an integer, and then we just use the fractional, just replace n by some a, and we just, then we justified everything. So the idea was originally really from the paper with Rahman. And well, after you do that, you get this. Now, okay, so what happens here? Well, what happened, okay, also, sorry, I forgot to mention that there were other cases of computing this inverse in a paper with Malcolm Brown, and the first one was with Zhang. Okay, so now here is what the operator is finally. Okay, so the operator acting on this is this one. This is the G, this is the special function that we chose. And this is the weight function for the q-Hermite, and is divided by this thing, whatever it is, this whole thing here. Sorry, this is the weight function for the q-Hermite, and 1 over this times that is the Poisson kernel. So it's just written in a explicit form. And then this is the dx, because x is cosine phi. And so this is what the operator is that we started with. Then again, if you go back and look at the classical fractional integrals, there were 2 operators. There were the Riemann-Liouville and the Weil, and they were adjoints. So we looked at the adjoint of this. And the adjoint of that is very easy. All you do is that this g that depends on x goes down, and this g that depends on y goes up. So that's what the adjoint is. The adjoint now is in a space with this weight function, the weight function for the q-Hermite. Okay, so we computed this one, and it's adjoint. And they're both semigroups. There are 2 semigroups. We computed the infinitesimal generators for both of them. And we computed their spectra. Now, it turned out that these operators were not normal operators. So you don't have really spectral theory. But anyway, we computed all their eigenvalues. More importantly, we computed their trace, because if the operator is not normal, the trace is not necessarily the sum of the eigenvalues. So we computed the trace, and these are the eigenvalues for the t. We computed the one for the adjoints. We computed the one for Suslov, which the one with Suslov, the computation is already in Suslov. I mean, he didn't write it down explicitly, but it's there. It's, if you look carefully, you can figure it out. But we computed the one and the adjoint, the one for these operators and their adjoints. And okay, so that's what this is. We also proved that these operators are contraction maps. It's not true in general as a contraction map. However, there is a condition here which has to be necessary, because your norm is at least as big as the smallest eigenvalue. And the smallest eigenvalue here is when m is 0. So this term is 1. But this is not, I mean, this can be bigger than 1 for small q. So you want the assumption that this thing, without the a, of course, is less than 1. And this is necessary and sufficient for being a contraction map. So it turned out that it's a contraction map if and only if lambda 0 is less than 1. Okay. Now, Suslov's case, the operator is Hermitian, so there is no problem. And we did some more calculations, because we wanted to calculate the action of these fractional integral operators on like powers of x, or what corresponds to powers of x. These functions, these polynomials, were introduced in a paper with Dennis Stanton, 2003. In that paper, we were doing Q-Taylor series, and we used this as a basis, and we have a theory of how to expand functions into this basis. Now, this here a product from 0 to n minus 1, but I want n to be general. So I can write it as integral from 0 to infinity divided by the integral from n to infinity. If I do this, I get this thing here. Okay, so if n here is a natural number, this will become like that. If n is not phi 0 is 0 here. So this is starting from 1. If n is not a natural number, this makes sense. So that's our definition for generalized powers. This is the definition of like x to the alpha. And what happens is that if I act with this operator on this thing with beta, now beta is not necessarily an integer, you see, I get alpha plus beta. So it's exactly like fractional integrals. Fractional integrals, if I differentiate x to the n over n factorial, I get x to the n plus 1 over n plus 1 factorial. And if I take the partial, the integral, the fractional integrals, I increase this by alpha and I can change this. So this formula is the exact analog of this. So this plays the role of powers indeed. And we got this to work. And then we also used this TA to derive what's called transmutation relations or connection relations. Okay, so what's the connection relation? I have two families, Pn and Qn of polynomials. And I want to write Pn as an integral of Qn times something that does not depend on n. Okay, so if I have the same family, if I have an AskeyWilson family, this can be an AskeyWilson with set of parameters, and this is a different AskeyWilson with a different set of parameters. And I can write down this connection. Okay, so in our case, we couldn't do the general AskeyWilson. We did two parameters. It has two parameters, but then the first two, our techniques don't work unless we make these choices. I mean, I wish we can remove this, but we can't. And for this one, if I take the TA acting on this, I get another AskeyWilson. So that's the transmutation relation that we found. There's a similar one for the S's. It does the same kind of thing. And you can also solve certain analogs of dual integral equations using this technique. So you can do all kinds of things with it. Again, there is similar theory for the adjoints, the same stuff. And we are still trying to understand what's going on here, and we don't know yet how far we will go. Now, one thing that we do not know how to do is an analog of Leibniz rule. You see, Leibniz rule here is for derivatives, and for the old Q difference operator. Sorry, there are old papers by Osler, Aslam and Verma and Nabi Mansour. There are quite a few papers on fractional powers of the derivative and of the original Q difference operator, not the AskeyWilson. And we don't know, so they have not only this, but they also have fractional powers here. And we don't know how to do this for the AskeyWilson, although we know what the fractional powers look like, but we just don't know. Another thing we're keeping in mind to do is about the Dunkel operators or elliptic cases, like the kind of things that Eric Rains are looking at. Again, this is very early in the development, and we don't know how far it will get. So this is where things are, and as you see, the story is still unfolding. There are quite a few things that we don't know. Important questions to describe the images, the ranges of these operators when the domains are certain space, like Like if it's LP, what is the image of LP under these maps? Can you describe inversion formula, which is like the one for the fractional integral operators, like this one. You see the idea for the fractional integral, you have an order which is not an integer, so you write as an integer plus something, and then you hit it with the I, so the a cancels, and this becomes n plus 1, and then you differentiate n plus 1 times to get the function. So this here goes word for word. I mean, the same thing works. You just replace this by your operator, this by your operator, and this is by this other operator that you are taking fractional powers of the inverse. So the inversion formulas we computed, and in particular, we showed that these maps are one-to-one. Otherwise, you cannot do the inversion. And we don't know much of a spectral theory yet. Again, the problem is that we don't know how to describe the ranges of certain spaces under this. For L2, most of the stuff that we did is either L2 or for continuous functions. In general, we have no idea what the picture is, and this is where the hard problems are. It's for general. Okay, I think I'm done. All right, thank you. Okay. Hello?
Hello. Stop sharing.
Stop sharing.
Yeah.
Okay.
There you go.